Hello everyone, in this video I'll be explaining some chemical reactions of alcohols and phenols. Now the first reaction, the reaction with active metals. Now if we check the reaction of active metals, alcohols and phenols, they react with active metals like sodium and potassium to give alkox, the alkoxide of the metal with liberating hydrogen gas. Now if we take an alcohol, 2 moles of alcohol and then 2 moles of sodium, it will give us sodium alkoxide. And then hydrogen gas will be liberated in the reaction. This is known as our sodium alkoxide. Now for example, if we take 2 moles C2H5OH, this is our ethanol, sodium, it will give us, this is known as sodium ethoxide. And then hydrogen gas will be liberated out in the reaction. Now thus here the hydrogen atom of the OH group, we see here that the hydrogen atom of the OH group in alcohols is displaced by the active metal sodium. Now this reaction shows that hydrogen atom of the OH group in alcohol is acidic in nature. Thus the acidic nature of alcohols is due to the polar character of the OH bond. However, alcohols, we know that alcohols are weaker acids than water. Now, for phenol here, we take our 2 Na to give us sodium. This is our sodium phenoxide. This is how our alcohols and phenols react with active metals. Now the second reaction is esterification reaction. Esterification reaction. Now in esterification reaction, here alcohols react with carboxylic acid. Our alcohols react with carboxylic acids in the presence of concentrated H2SO4 to give us esters. This reaction is known as esterification reaction. Now this reaction is known as esterification reaction, and here it involves the cleavage of the OH. There is cleavage of the OH bond in alcohol. Now let's check out this reaction. So we have, let's take an carboxylic acid and then H. There is cleavage of the OH bond in alcohols. Therefore, this bond will be cleaved off, and then there will be removal of a water molecule in the presence of concentrated sulfuric acid. Concentrated H2SO4 to give us an ester, that is C double bond OR dash. This is known as an ester along with water molecule. Now taking an example here, let's take an acid CH3COOH plus HO C2H5 in the presence of concentrated sulfuric acid. Now there will be cleavage of the OH bond in alcohols. That means the OH bond will cleave off. Therefore we will be get, this is our ethanoic acid. Ethanoic acid, it is commonly known as acetic acid. This is our ethanol, 2 carbon atoms, and then we will be getting here our CH3CO or C2H5. This is known as our ethanoid. This is an ester along with a removal of water. Now this esterification reaction is a reversible reaction, and thus the reaction should be carried out in the presence of a dehydrating agent like our concentrated sulfuric acid, because our concentrated sulfuric acid removes water as soon as it is formed. Now let's see acetylation reaction, that is reaction with the acid anhydrides and acyl chlorides. That means addition of the acyl group into our alcohols. Now alcohols, when treated with our acyl chloride, suppose we have here our, let's take any acyl chloride, CH3 C double bond O Cl. This is known as acetyl chloride. This is known as 2 carbon atoms, therefore it is ethanol chloride. Plus, let's take ethanol again. Ethanol in the presence of pyridine. When alcohols react with acyl chlorides or acid anhydride. Okay, let's take the first one, acyl chloride. When alcohols react with acyl chloride in the presence of pyridine as catalyst, they give esters. Here also it will be the cleavage of the OH bond in alcohols. Therefore, we'll be getting here also esters, CH3 C double bond O C2 H5, and then HCl. HCl is removed in the solid. This is also known as ethyl ethanoate. Now, when alcohols react with acid anhydride, there, this is acetylation reaction. Addition of the acyl group. When acetic anhydride or acetyl chloride is used, the reaction is called acetylation because the OH, the hydrogen atom in the OH group of alcohol is replaced by an acyl group. That is, the acyl group is CH3CO by this group. Hydrogen atom is kick off, and then in the position of hydrogen atom we add this acyl group. Therefore, acid anhydride, let's write acid anhydride. This is our ethanoic anhydride, or this is known as acetic anhydride. When it reacts with our ethanol, there will be the cleavage of this. Let's take this bond, and then we'll be getting here in the presence of pyridine again. We'll be getting here CH3 C double bond, or this group will go and join, will replace the hydrogen position, and then we'll be getting O C2H5 plus, and then this hydrogen atom will go and join with this group, giving us an CH3COOH. This is our ethanoic acid, and this is also our ethyl ethanoate. Therefore, in this way, this is the formation of esters when we use acyl chlorides. When you use acetyl chloride and acetic anhydride in the presence of pyridine, there is cleavage of the OH bond in alcohol, and there is addition of this group in the position of the hydrogen, that giving us esters. Now, let's check the third reaction, that is reaction with halogen acid. Reaction with halogen acid. Now here in this reaction, when we check out the reaction with halogen acid, we will see that our alcohols reacts with halogen acid to give us, halogens will react with our halogen as alcohols reacts with halogen acid to give us our X plus H2O. Now here, in the reaction of our alcohols with our halogen acid, we will see that the X can be Cl, Br, or iodine. Now, on treatment of our halogen halide, an alcohol will give us a haloalkane. Now, when we check the order of the reactivity of this halogen acid, our hydrogen iodide will react more vigorously than hydrogen bromide, than our hydrogen chloride. Now, and the reactivity of alcohols would be, tertiary alcohol would be more reactive than secondary, than primary alcohol. Now, the reactivity of HCl is lower than that of HBr, than that and HI. And primary and secondary alcohols are more. Primary and secondary alcohols react with HCl only in the presence of a catalyst. That is, our primary and secondary alcohols reacts with HCl. Okay, our hydrogen chloride only in the presence of a catalyst, that is anhydrous zinc chloride. The reaction with However, the reaction of HCl with our tertiary, now let's say our primary and secondary, reacts with HCl only in the presence of zinc chloride, whereas tertiary alcohols, the reaction of HCl with tertiary alcohols does not require the use of this catalyst. Now, to study this reaction, let's do for one example first. CH3, CH2OH. This is our ethanol. Ethanol reacts with 2 moles of HI in the presence of red phosphorus to give us CH3, CH3, and ethane along with I2 plus H2O. Now here, another example. Okay, let's take our primary alcohol C2H5OH reacts with HCl in the presence of zinc chloride to give us C2H5Cl, a haloalkane, a water molecule. Now, to study this, the study of this is given in the form of a Lucas reagent. Lucas reagent, that is mixture of anhydrous, ZnCl2 zinc chloride, and concentrated HCl, which is used to distinguish between primary, secondary, and tertiary alcohols. Now let's check out the reaction of this Lucas test. Now here, primary alcohol. Let's take for first primary RCH2OH when it reacts with concentrated HCl and anhydrous zinc chloride. There is no reaction. Now no reaction occurs, and hence here to distinguish between primary, secondary, and tertiary, the product that is obtained will have a white cloudiness or turbidity is to appear if the reaction persists. But primary alcohols, when they react with our Lucas reagent, no reaction occurs. Now when we see secondary alcohols are CHOH. In secondary alcohols, we will see that when it reacts with our Lucas reagent, they will give us RCHCl. Now here, white cloudiness or turbidity appears within 5 minutes. But in primary alcohols, we have seen that there was no turbidity or no reaction. Here there is turbidity in 5 minutes. Now for tertiary alcohols, our tertiary alcohol, when it reacts with Lucas reagent, are a tertiary haloalkane. Now here the turbidity appears immediately in tertiary alcohols. Thus, with the help of Lucas reagent, we can distinguish between our primary, secondary, and tertiary alcohols, because in primary, when our primary alcohols reacts with Lucas reagent, there is no reaction and thus no turbidity is formed. Whereas our secondary alcohol, when it reacts with Lucas reagent, turbidity appears in 5 minutes. And tertiary alcohols, when it reacts with Lucas reagent, the turbidity will appear immediately in our tertiary alcohol. Therefore, from our Lucas reagent, we can study the differences between primary, secondary, and tertiary alcohols. In the next video, I'll be explaining more chemical reactions of alcohols and phenols.